Um, Casey Bravo, he is an undergraduate student working with Professor Sarah Posey. His presentation is validating organic scintillator rho-C alpha measurements of fast metal assemblies using simulations. Go ahead, Kasia.
Hello, everyone. Thank you for having me here today. Can you hear me all right?
Yes, we can.
Let me just hide this little thing here, thumbnail. All right, hello, everyone. My name is Kaiser Bravo. I'm a rising senior at the University of Michigan studying nuclear engineering and radiological sciences. I work under Professor Sarah Pozzi, and my mentor is Michael Hua, who just presented. Today, I'll be presenting on validating organic scintillator Rossi alpha measurements of fast metal assemblies using simulations. So to begin, the K-effective describes neutron multiplication within a system, or the intergenerational ratio of neutron gains and losses. However, we cannot measure this directly, so we use Rossi alpha measurements to estimate the prompt neutron decay constant alpha, which we then use to infer the K-effective. Historically, we have used helium-3 gas proportional base counters to perform this work, but previous work has also shown that their microsecond systems are insensitive to the inverse alpha, or the lifetime of the neutron of fast assemblies, which works on the 10 of nanosecond scale. And thus, faster detection systems based on organic scintillators are of interest to augment the current Rossi alpha toolbox. And so the focus of this work is how we validate organic scintillator-based Rossi alpha measurements of fast metal assemblies by comparing measurement to two different independent simulations. This work is relevant because measurements of reactivity and the K-effective multiplication factor of special nuclear material assemblies are crucial to nuclear nonproliferation, safeguards, and criticality safety. In particular, criticality safety monitoring uses K-effect to prevent accidents. Infamous accident is Lewis-Slotin criticality accident, as shown here on the right, where plutonium hemispheres were separated by a mere screwdriver and ended in death. So to begin, the focus of this work uses Rossi alpha, which is a microscopic neutron noise method, which takes a pulse train of neutron signals, as shown here in the inner box on the right. And from this train of neutron signals, we can have correlated and uncorrelated neutrons in time, and we figure out how correlated they are by finding the time difference between them. In particular, we use a type 1 spinning time difference, which takes a window and takes the first neutron in that window and takes the difference between it and every other neutron in that window, and does that and shifts it all along until we have time differences between all neutron detections. And using a bin width of 1 nanosecond time differences, we obtain a histogram between all neutron detections. And this is the Rossi alpha histogram as shown here in the larger plot. From this larger plot, the prompt neutron decay constant alpha can be fitted using a double exponential in particular for our work, and using the equation here as shown, we can relate the effective delayed neutron fraction and the mean neutron lifetime to the K effective and reactivity. The effective delayed neutron beta effective and mean neutron lifetime lambda are typically determined through simulation, however. And the detectors used in this work are organic scintillators. Particularly, we have been using trans-Steelbeam crystals, as shown here on the right. And we use these because they're capable of detecting both fast neutron and gamma rays, but we're more interested in how these scatter-based recoil detectors are sensitive to fast neutrons without moderation, as has been said on many presentations before. Their wide neutron energy range is very useful, and their nanosecond timing capabilities allow us to measure things a lot faster as compared to the helium-3 systems, and the pulse shape discrimination is very useful when needed to be implemented to separate certain events. So this measurement begins with a 4.5 kilogram of alpha phase beryllium reflected weapons grade plutonium called the burp ball. And we use this in 5 different reflector configurations, starting with the bear case and then 7.62 centimeters of iron, copper, tungsten, and nickel as reflectors. All these measurements were performed at the National Criticality Experiments Research Center, NCERC, at the Device Assembly Facility. This work has used two 12-trans-Sylvian scintillator arrays and two nomad detectors. And then using these measurements, we then calculate the alpha, as we did before with Rossi alpha, and then we perform two different simulations on it. So using KOPS, which is an MCMP code, we simulate the beta and the lambda, and that combined with the measured alpha, we then deduce the K effective measured. And then we compare this K effective measured to the MCMP K code simulated K effective to then compare the K effective between the measured and simulated assemblies. And then for more direct comparison, we have the simulated alpha, which uses time bin tail fit, which has a surface tally using MCMP's code to then compare the inverse alpha of the measured and simulated assemblies directly. Here is the experiments on simulation setups on the left. Something to note is that although all four arrays are present, we've been only using 12 trans-Sylvian detectors to prevent any crosstalk that's happening. And we're measuring and these setups are representative of all 5 different reflectors with 30-minute measurements. On the right is the MCMP model, representative of all the scenarios, which will be used with our equation from before to deduce the 2 true/known values of alpha and the K effective. And these are the results. For ease, we compare inverse alpha to compare units of time. And as shown here on the right, the measured and simulated confidence intervals overlap as 1 sigma for iron, copper, and tungsten cases, 1.02 for nickel, and 1.31 for the bare case. Overall, this is a very good agreement between the measured and simulated inverse alphas and has a general trend, except for the case of iron, of the measured slightly overestimating the inverse alpha. And because we know that they have good agreement, it helps us when we have the measured values of alpha to infer with the KOPS simulated values of beta effective and lambda to infer the K effective measured, as we will do with the next simulation. So using MCMP's K code criticality source card, we can calculate the K effective simulated and also obtain uncertainty for that case. Using the equation from before with the alpha from before, the K effective measured and K effective simulated can then be compared, shown here on the right. The measured estimates of K effective are less than simulations calculated, except for the iron case, and this is probably due to the iron case having a plug missing to prevent criticality, and the error uncertainty in the K effective increases as the K effective simulation decreases. However, this is expected since the point kinetics model assumes that the K effective is approximately 1, and thus would perform worse for more subcritical systems. And the expected impact of this work is that if successful, this work will contribute to the phasing out of slower detection systems in favor for fast systems such as organic simulators. Furthermore, the validation of the 2 exponential model opens the door to explore various shielded and reflected assembly configurations, as well as various geometries, and allow us to learn more about increasingly smaller masses to counter smuggling of special nuclear material. And in conclusion, from these measurements of the burp ball in 5 different configurations of bare, copper, nickel, tungsten, and iron, we have performed analysis with the 2 exponential Rossi alpha model and found good agreement between measured and simulated values of alpha. This work shows that the organic simulator-based systems are sensitive to fast assemblies, and because of this, organic simulators should replace CM3s in fast metal applications. Furthermore, the 2 exponential model adequately describes the physical phenomenon using two-region point kinetics. Next steps for this work include validating the models for both helium-3 based and organic simulator-based systems for general reflectors. And furthermore, the comparison of both systems in time-correlated microscopic neutron noise methods of other kinds. MTV has had a great impact on me over these few years. They have funded my work across several projects, doing so happily. They provided me the opportunity to be a summer fellow multiple years They have connected me with Los Alamos National Lab for an internship, which I'm currently working at now, and have allowed me to follow the development of the organic simulator capabilities at NSERC. It has been an amazing time. I'd like to thank the Consortium for Monitoring Technology and Verification, the NNSA, and DOE for supporting my research activities. Thank you for your time. Are there any questions?
Thank you. Thank you for the good presentation. Are there some questions from the audience? I don't see. So I have a general question, Cassie. The organic scintillators has been around for a long time. So what has been the challenges that people move from, say, helium-3 based systems to this organic scintillator-based system? Why they have not done this work earlier? So what's their challenges?
As far as I know, right now I don't know for sure why it hasn't been done before, but I know that now we are doing the work to see that they are verified and validated. But it's probably due to we have the technology now to actually cast and grow these still beam crystals more easily than previously before. Because helium-3 was a byproduct of the weapons program, so it was readily available.
There was a question posted by Roger. Did the slide stop? This is not specific to you, Cassie. Did the slide stop updating for anyone else? I have not seen it stopped. So I looked. Presentation has been going well. So I don't know whether there's other problems for some of the audiences. Okay. Are there other questions? And people should feel free to ask questions using your microphone if you have any. If not, thank you, Cassie. Thank you for your good presentation. Let's move to the next student.